From moment zero to today, our universe's story has been one of creation. As the energy of our universe fragmented into everything from the fundamental forces to the fundamental particles that built up and hold together everything that exists. Understanding exactly how we went from a universe of pure energy to today's lumpy, luminous reality has not been straightforward. Until relatively recently, we could only see the nearby universe in detail. Our understanding came from running theoretical models from moment zero forward, while observers worked from now to see things long ago. Part of the problem we faced is the expansion of the universe stretches out light waves. The hydrogen light you might see from the sun using a solar telescope gets shifted all the way into the infrared as it travels to us from the first billion years of the universe. To see this light well, we had to wait, and wait, and wait some more for JWST to get built. And now that we have the JWST, suddenly we're able to see not just how galaxies formed early in time, but we're also able to see new details in star and planet formation. Combining this data with additional discoveries from everything from other telescopes to gravitational wave detectors, the rate of discovery is wild. Reading through journal articles sometimes leaves me feeling like we all need to take the approach of the Red Queen and be prepared to believe 6 seemingly impossible things before breakfast. In this episode, we look at some of our latest discoveries about the formation of star systems, including planets and moons, and the growth of black holes. And we celebrate that the JWST resides out beyond the moon's orbit, because our ability to observe from the surface of our planet is getting thwarted by a growing swarm of satellites that may soon include massive reflectors, literally designed to turn night into day. Let's take a look at what we can expect if these wildest plans for the future become our reality. I am Dr. Pamela Gay, a senior scientist at the Planetary Science Institute, and you are watching Escape Velocity Space News, an independent science news show funded by you through Patreon. Our universe has a frustrating habit of hiding its light, especially the light of star formation. Stars, including our own sun, form in massive clouds of dust and gas, with the first stars igniting in the cloud's densest regions. Unfortunately, as anyone who's tried to drive in a dust storm or fog has learned, clouds are very good at scattering light, with blue light scattering much more easily than red and infrared light. When we look at star-forming regions like the Orion Nebula, we're seeing places where the largest stars have fully formed and their light is already clearing away the material around them. When we look at systems like the pillars of creation, where stars are just starting to form, the situation is very different. To a telescope that sees the colors observed by our eyes, like the HST, these clouds are completely opaque. It is only as we look at them with infrared light that we begin to see the youngest stars. And the JWST just observed its largest and youngest star-forming cluster. Located just a few hundred light years from the center of our galaxy, this cloud is named Sagittarius B2. It contains just 10% of the galactic core's star-forming material, but is responsible for forming nearly half the region's new stars. In near-infrared images, the region is a mix of inky blackness with bright clouds of star formation. At longer mid-infrared wavelengths, starlight shines brightly with only the thickest clouds still visible. While the mix of atoms in the star-forming region is different from the stuff of the early universe, this chaotic region still gives us our best view to date of star formation in a dense cloud. This work is led by Nazar Bedevim, and a preprint posted in archive.org describes how JWST's observations are allowing researchers to study how light is able to push its way free from dense clouds, and how differences in densities allow systems to appear different in optical, radio, and various shades of infrared. According to ESA, astronomers hope Webb will help them better understand the process of star formation in this dense galactic center region. Has it been going on for millions of years? Or has some unknown process triggered it only recently? As analysis of this data continues, we'll bring you updates on this story. Observing planetary formation can be a struggle. Stars are bright, and planets on all but the largest orbits can get lost in their glare. But not all planets form around stars. We knew this from theories, and now we know it thanks to observations from the ground-based Very Large Telescope in JWST. A rogue planet has been found roughly 620 light-years away in the direction of the Chameleon constellation, with between 5 and 10 Jupiter masses of material. It's nearing the boundary between a planet and a brown dwarf, but it is clearly a planet. Material is falling onto the planet at an accelerating rate, with infall recently measured at 6 billion tons per second. According to team researcher Alamedratus Abad, quote, "This is the strongest accretion episode ever recorded for a planetary mass object," end quote. The wild inflow of material is thought to be enabled by a magnetic field. This, along with changes in what materials were seen in the disk, are things we've only seen in stars before, and these observations seem to indicate that rogue planets have the ability to form the same way stars form. This now gives us 3 different ways to form rogue planets. They can form in a planetary disk around a star and then get stripped out. They can form in an eddy with 2 solar systems sideswiping each other. And they can just form. While we are getting better at seeing planet formation, we are still struggling to catch details as fine as moon formation. But we are getting there. New JWST observations of a 2-million-year-old baby star have identified a massive planet with its own surrounding disk that is primed to form a moon. According to Sierra Grant, quote, "We can see evidence of the disk around the companion, and we can study the chemistry for the first time. We're not just witnessing moon formation, we're also witnessing this planet's formation," end quote. Grant co-led this project with Gabriel Cogno. The planet and disk are about 15 times further away from their star than Neptune is from our sun. Close into the star, nothing more complicated than water stands out. But in the planet's disk, researchers have seen acetylene, hydrogen cyanide, ethane, benzene, and more. These observations support our hypothesis that Jupiter's moons could have formed as part of a disk surrounding the large planet. And this is just the start. In the coming year, JWST will be observing the physical and chemical properties of similar objects. And when those results are published, we'll bring them to you right here on EVSN. Before we go to break, I want to bring you a quick update from the LIGO-Virgo-CaGRA collaboration of gravitational wave detectors. By studying amplitudes and frequencies of the incoming gravitational waves, it's possible for researchers to calculate the rough masses and even rotations and distances of the merging objects. 2 recent black hole mergers provide solid evidence that smaller black holes can merge over and over into larger and larger systems. In one system, they saw a 20 solar mass and a 6 solar mass black hole merge. The larger black hole was also one of the fastest rotating black holes so far seen. It is easy for merging objects to end up spinning very fast, and the 20 solar mass object is likely the result of one or more mergers of smaller black holes. In the other system, a 17 solar mass and 8 solar mass pair of black holes merged together. Weirdly, the larger system was rotating in the opposite direction to how it was orbiting, something that is just not expected. Again, it appears the larger system's odd appearance could be the result of earlier mergers and a late combining into the black hole binary system that was just seen to merge. This kind of a series of mergers is possible in very dense star clusters where objects can pass close enough to join into new binary star systems and get flung out of multi-star systems over time. This also fits in well with growing evidence for intermediate mass black holes in clusters. All in all, this is just one of those nice results where what we see matches what was expected. After a break, we're going to take a look at weird things that are going to make observing our sky harder in coming years. Stay tuned. Folks, we live in interesting times. At least once a day, I find myself Googling something I've read to see if it is real or not. The next two stories have each taken their turn making me Google. And they're both true. Story 1. Reflect Orbiter has secured both Series A funding and a NASA Small Business Innovation Research grant to develop maneuverable space reflectors that can turn night to day in the hours around dawn and dusk. Altogether, they plan to launch 4,000 18-meter by 18-meter reflectors into sun-synchronous polar orbits. Each mirror will orbit in about 100 minutes. Individually, they won't have the ability to provide light to any one location for very long. But working together, they believe this constellation will make it possible to light up everything from solar panels to industrial sites, to large events, to, and this one I'm okay with, to lighting up natural disaster sites where extra light can make it easier to save lives. When not directing light at a specific location, they plan to tilt their mirrors away from Earth to prevent stray light from going where it isn't requested. Side note, their website implies that folks will be able to reserve sunlight with a cell phone app. This is the weirdest Star Trek future. It's unclear how well this will work, but we're likely to find out next year. They're currently planning to launch a test unit in April 2026. There are several technical issues they'll need to sort to be successful. For instance, they'll be regularly rotating and tracking an awkward frame of mylar in much the same way that we currently steer space telescopes. With a large moment of inertia, these systems will be demanding on their servos. They will also experience a highly variable amount of drag and will need to adjust their orbits regularly. These are just engineering difficulties, however. What is harder to understand is how they will be able to focus light as precisely as they claim. According to reporting by Space.com, they anticipate that within 10 kilometers of an illuminated site, the satellite's light will be undetectable. But there's a lot that can go wrong. We know that animals and people are both very sensitive to stray light and light pollution and can suffer everything from behavioral changes to health problems. It is unclear what effects illuminating solar farms for extra hours will have on surrounding life. And we can't know for certain how well they'll actually be able to turn on and off at just the intended location without painting the surroundings with light, or if they'll truly be invisible when rotated away from Earth. There is also the potential for these satellites to break in an orientation that will misdirect light over and over at the same locations. Again, turning night into day. Locations that may not want to be bright. Now add in all the chaos of making sure that pranksters can't order up light for dark sky sites, observatories, and Other places that, again, would rather not have their night turned into day. There are a lot of concerns with this kind of technology. Software bugs happen, and servo failures are a common problem for satellites. I do not want to witness both of these kinds of issues becoming an issue for satellites designed, say it with me, to turn night into day. Satellites are already a problem when we try to observe the night sky. 4,000 more that are designed to, again, turn night to day. Well, I'd like to see us find another way to power our world and illuminate recovery sites. Anyway, April 2026. Stay tuned for missions that light the night. And speaking of lighting the night, during the last 2 Starship launches, the broadcast hosts highlighted plans to launch more than 10 times per day, with Musk previously stating they wanted to build a Starship in as little as 8 hours. I admit, I didn't question these numbers. We've heard a lot of numbers thrown around over the years, and at a certain point, I decided to watch the data instead of listening to promises. But then I saw a picture of a jellyfish of light created by rockets firing in the upper atmosphere with the caption, "Imagine a whole sky lit up with these." The writer was actually excited. But as an astronomer, this idea stopped me in my scroll and made me ask, under exactly what circumstances would we have a sky full of starships? Well, when you run the math on SpaceX's Mars plans, this is required for them to build their colony of 1 million people. Per SpaceX's website, starting as soon as 2026, SpaceX intends to launch thousands of starships toward Mars during the every 26-month launch windows. This is going to require a truly horrifying number of launches. Consider the amount of steel involved alone. Each Starship has conservatively 80 tons of steel. 1,000 Starships is 80,000 tons of steel. While that is only 0.1% of the U.S. yearly steel production, that is 0.1% of the U.S. steel production that we would be sending to Mars. And each of those 1,000 Starships that might go up each launch window, they're going to need to be refueled on orbit, with the number of estimated flights needed for each refueling ranging from 6 to 60, depending on just whose numbers you use. Conservatively, assuming it is 19 launches per Starship, just to fuel each ship, you're looking at 20,000 launches in 26 months. That's 25 launches per day, which is admittedly more than 10, but when SpaceX said they plan on more than 10 launches a day, I was thinking like 12, not more than 24. When they discuss needing to produce a Starship every 8 hours, they mean it. These are the numbers required to accomplish the 1 million people and millions of tons of cargo on Mars visions that SpaceX has laid out. Musk and others have argued that we need a colony on Mars to serve as a backup of the human race. But there is irony in destroying our environment in the process. And during the 2-month launch window to Mars, if they do launch those 1,000 Starships, we'll see roughly an engine firing every 1 to 2 hours as each Starship fires its way out of low Earth orbit and heads towards the red planet. And that is a whole lot of light, likely on the midnight side of Earth. And that's light that will be interrupting any attempts we may still be making to observe the stars from Earth. I have to admit, my desire for the easy launch of massive space telescopes and heavy multiplanetary explorers is currently at war with my desire to be able to see the stars from my roof. I don't know how this story will end, but it feels like right now we can have one or the other. We can have dark skies, or a sci-fi future. After the break, we'll be back to take a look at this week's Tales from the Launch Pad. Stay tuned. Next up, I'm pleased to welcome on aerospace correspondent Erik Madaus for this week's Tales from the Launch Pad. Hey, Erik.
Hi, Pamela. On October 13th, SpaceX launched the 11th Starship flight test from their South Texas spaceport. Let's watch the launch.
5, 4, 3, 2, 1. We have liftoff. Go Super Heavy. Go Starship. Thanks for all the historic flights, Pad 1.
Vehicles pitching downrange. Booster Raptor chamber pressure nominal.
The flight had the same basic profile as the ones since Flight 7. Go up, deploy some metal sheets representing Starlinks, re-enter, and land. It more or less worked similar to Flight 10, but with less noticeable hull damage after re-entry. The first stage booster flew a less aggressive trajectory than Flight 10 and did not explode during the landing burn. It landed a few hundred feet into the air, simulating a catch, and then broke apart on ocean impact as planned. The next Starship launch will not be for many months, as SpaceX needs to finish Pad 2 to support the next version of the Starship vehicle. On October 14th, Rocket Lab launched the Strix 7 satellite from their Madaus spaceport. Let's watch the launch.
5, 4, 3, 2, 1.
Beginning pitch over.
The mission was called Owl New World and was Rocket Lab's 9th launch for the company since Bactive. On October 25th, JAXA launched the first HDV-X spacecraft to the ISS on an H3 rocket. Let's watch the launch.
All systems are go. Main engine start. The main engine ignition.
1、0、1、
SRB3 点火。Lift off. Solid boosters are ignited. Lift off.
6、7、8、
HTVX-1 を搭載した H3 ロケット7号機は2025年10月26日午前9時00分15秒に種子島宇宙センターから打ち上げられました。We have a successful liftoff of H3 launch vehicle flight number 7 with onboard HTVX-1 from JAXA Tanegashima Space Center at 9 o'clock a.m. and 15 seconds on 26th of October 2025, Japan Standard Time.
HDV-X is an improved version of the HDV uncrewed cargo vehicle, which Japan launched 9 times between 2009 and 2020. It can carry more cargo than the HDV and can be loaded as late as 24 hours before launch, unlike HDV. Unpressurized cargo is handled by placing it in the new service module instead of inside the spacecraft. A variant of HDV-X called the HDV-XG will be used to resupply the Gateway Lunar Space Station. Launch was successful and the spacecraft took 3 days to rendezvous with the ISS. It was grappled and burst to the ISS by JAXA astronaut Kimiya Yui and NASA astronaut Zeta Cardman. Big Mega Constellation update this week. SpaceX launched 8 batches of their own Starlink satellites and 1 batch of Kuiper satellites for Amazon. Over in China, there was 1 batch each of the SetNet Leo and SpaceSail constellations. SpaceX also launched Layer C of the SDA Tranche 1 communications satellites for missile defense. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the United States has had 151 launches, China has had 68 launches, New Zealand has had 13 launches, Russia has had 8 launches, Kazakhstan has had 5 launches, French Guiana has had 4 launches, India and Japan each have had 3 launches, Australia, Israel, and Norway each have had 1 launch. This makes the total number of launches so far this year 258. Of these 258 launches, there were 10 failures, reminding us space is hard.
Thanks, Erik. Before we go, I need to tell you about my new favorite way to explore Mars. A relatively new company, Tumbleweed Mars, has a logo that looks a bit like a Death Star. So of course, I clicked their logo, and I discovered a delightful website. I learned of a new way to explore the landscape, the Tumbleweed rover. Designed to catch the wind and tumble across the landscape, this lightweight system can collect data over a large area at low cost. Recent wind tunnel tests have shown that wind speeds of just 20 miles per hour are capable of setting the rover in motion across rough terrains and even up 30-degree slopes. In addition to their wind tunnel tests, they also have taken an early prototype out into a quarry in the Netherlands, near where they're located. That simple field test demonstrated they can gather data on the go. In future work, they'll be adding more instruments and taking it out to the Atacama Desert. One day, we may see tumbling rovers measuring radiation, checking out soil and dust, and collecting weather readings on the red planet. I'm here for this kind of creative exploration. And that's it for now. Good night, everyone. And remember to go out and look up while you can still see the stars. And also, remember to click the video's like and subscribe so the algorithm tells you and the world when new science is ready to be learned.